So we'll have our next speaker, Soham Chakraborty, and he will be talking about interesting topic. Everyone talks about, I have 200 clusters, with 3,000 Kubernetes services over 16 regions. And he'll be talking about what will happen if you manage this on small scale. Like small scale, well done Kubernetes. And that's a topic that not many people talk about, and I really like this. I'm really looking forward for this one because everyone, is trying to say, I have big one, I have like gazillion of clusters, and we're doing like this big scaling. I'm interested about the talk, hey, I have just small cluster, and I'm trying to make it perfect, and that's what Soham will bring us. I hope that you are ready. Are you ready? You don't seem to be convinced, but let's try. Okay, so stage is yours.
Thank you, Mark. Is it audible properly? Everything? Cool. All right. Hello, everybody. My name is Soham, and welcome to the talk, Lessons Learned from Operating Small-Scale Kubernetes Clusters. I work at a company called Sematext. Remotely, it's a US startup. So very briefly, as Marek said, that I just want to take a moment to actually say that why this particular talk. And the reason is that in most of the conferences that I have been to, people talk about Kubernetes on an astronomical scale, millions of pods, thousands of nodes, hundreds of ArgoCD applications. And I thought that I may not be the only person who doesn't use Kubernetes on such a scale. So there may be people like me, others who run Kubernetes on a much smaller scale or medium scale. So why don't I try to actually say what we are doing and what kind of challenges we are solving? So that's kind of the genesis of this talk. Brief speech about Sematext. We run an observability software as a service for our customers that doesn't cost you an arm and a leg. It's entirely bootstrapped, very small company, and running successfully for the past 15 years or so. So that's pretty much about me and where I work. And then let's see. OK. Statutory warning. This is entirely human-made, me-made content. No AI was involved or nothing was harmed. And any hallucination in this slide should be attributed to me, not any AI. All right? So this is what we're going to talk about. We'll define what I mean by small scale. What's the definition of small scale? We'll briefly touch upon kOps, the cluster management tool that we use. We'll see what kind of infrastructure components that we use for flow or clarity in this talk. We'll discuss the challenges and solutions. We'll spend a fair bit of time on cost optimization, and we'll leave some time for Q&A. Okay, so this is what our agenda is. Small scale. So at this point of time, we run 3 kOps clusters entirely self-hosted on AWS, spread over 2 AWS regions, 35 to 40-ish nodes most of the time, sometimes more, but that in that range. And we run roughly 300 pods in each cluster. So we are close to touch the landmark or threshold of 1,000 pods, but not there yet, so small scale. All right. Then, OK, how many people actually have used kOps or any show of hands? OK, only one. That's good. OK, so kOps is a tool for self-managing Kubernetes clusters. It's an open source tool. We started to use kOps before EKS, AKS, or those things came out. So we are using this thing since the inception of our Kubernetes journey, and it has performed fairly reliably over all those years without no major hiccups. With kOps, like as any provisioner, you have to do some sort of bootstrapping, like AWS VPC, Route 53, IAM, load balancers, those kind of things. But you have to do that across all your provisioners. There is nothing different in kOps. And then the important part is that you write a kOps manifest, which is nothing but a plain, simple YAML file, all right? And in that YAML file, you describe the state of your cluster, the intended state of your cluster, such as the version of the Kubernetes, what kind of CNI you are going to use, and everything. And then you do a kOps update, upgrade, or apply, however, and magically you have a Kubernetes cluster. All right? So it also has a nice, very nice CLI to interact with the cluster. And the plus point is that since it's an open source project, could be bugs or feature requests. So this has a separate Slack channel in the Kubernetes Slack itself where the maintainers hang out. So if you have a problem, you can actually ask and get traction there. This is the infrastructure components that we use entirely on AWS at this point of time, running on Spot instances. And since we use Spot, it's very cost-effective, but brings its own unique set of challenges, which we'll discuss later. Run our CI on Jenkins and CD and Argo, and Java and Go are the primary languages of choice, although we are trying to slowly phase away Java and move to Go. These are the lessons learned. I couldn't pack everything all together here because this will take the talk longer, and this is what we're going to talk about. Okay, so the first problem that I want to talk about is about health checks. So health checks, what are health checks? Health checks are essentially probes by which we tell Kubernetes as a cluster admin or user, we tell the kubelet when and how it should probe the containers running inside the pod and find out the status and health of the running containers, right? So there are a lot of different types of probes, but we are going to talk about readiness and liveness probes. The names are self-explanatory. And this particular problem revolves around what if we have an application that depends on another application. For example, take an example of a front end and back end. So if your front end is depending on your back end, you don't want your front end to start as long as your back end is not running. So you should have a readiness probe. You should have a readiness probe in your front end to check the status of your back end. When back end is up, your front end should be starting up. But at the same time, if you use the same endpoint for liveness probe, people use this health/health all the time. If you have the same endpoint, what happens if your backend is down? Your backend is down, and then your liveness probe will come in and restart the front end as well. Do you want that? No. Why? Because the front end is already running. Your backend is down, so you should investigate your backend, not your front end. So you have a separate endpoint to check the status of your backend. So that's why we found out it's very useful when you have a dependent application to actually have two separate endpoints. That's how you kind of avoid the circular dependency or cyclic dependency. This thing came for our Java applications when Java takes a long time to boot up and start. And the solution for this is to use something called startup probe. So as you can see, by the way, all of these screenshots and everything, this is actually from our actual use. So this is from our own cluster. No, nothing was made up. Here we are giving this particular pod 5 minutes to stabilize itself, and after 5 minutes, the readiness probe will start in. So the important point to consider is that your readiness probe should come in after your startup probe has completed. Otherwise, it will just kill the pod. This one, we used to have hard-coded secrets in our repository. There is a very nice article that is hyperlinked over here, which actually talks that how you should define your security strategy. The point is that you should actually find out how your environment, your application, your infrastructure is vulnerable, and depending on the level or vulnerability, you pick out the security solution, not the other way around. You should not pick up a security solution and retrofit into your environment. It should be, environment and then security solution. For us, the important aspect was not having any hard-coded secret in the repository, and we solved this particular problem with something called external secrets operator, by which we offload the secret to a secret store in your cloud vendor, and then external secret operator fetches the secret during runtime, and the problem is solved. Why we pick this up is that the external secrets operator is fairly simple. It's just one single pod by which you can run it, so the amount of code change was pretty minimal. Deployment or restarting application, you should try to see that your applications don't have much downtime or your customers are not affected. There are predominantly two deployment strategies in Kubernetes. One is rolling update and another is blue-green. rolling update is the Kubernetes native way. One pod goes down, another pod comes up. That's the philosophy, right? Which also means that simultaneously during rolling update, you have scenarios during which two versions of your application is running. This is by design, this is inevitable during the deployment process. And how you can tweak this? You can tweak this using some parameters called max surge, max unavailable. So let's take an example. So if you have a deployment with 8 pods, 8 replicas, and you define a max surge of 50%, you are telling Kubernetes that during the rolling update, you are allowed to go up 50% from the number 8, so 12 pods. And at the same time, max unavailable 50% means Kubernetes will respect the number 4. From 50% of 8 is 4. So during deployment or whenever, the number of pods should not go below 4. That's how you ensure your availability, right? It depends on testing, or your tolerance of failure. We found out these numbers work reliably well for us. This is one of my favorites, so that's why this has a meme. So who decides how much resource requests your application should have? Should it be the developers who write the code, or should it be the people who actually run the code? Now, we know that in DevOps, everything is simple, but everything is together. We are nice to each other. But the real world is not really that nice. It's a bit messier, so that's how we have this thing. So when this particular problem came to us, we started researching and landed upon this tool called Goldilocks. So Goldilocks is, again, an open source tool made by Fairwinds Ops. What Goldilocks does is that in Kubernetes, we have an object called VPA, Vertical Pod Autoscaler. And this Vertical Pod Autoscaler can automatically set resource request for your workloads. It can automatically come in and set the resource request. Goldilocks uses Vertical Pod Autoscaler with a small change is that it doesn't use VPA in the enforcing mode. It uses VPA in a recommendation mode. So, and it also provides a very nice little UI by which you can run Goldilocks, and then the resource request or recommendations will come up in the web UI, and you can actually check that and then set it up manually yourself, all right? I recommend that the numbers that Goldilocks shows, you should try to give a little bit of buffer on top of Goldilocks, the recommendations, because it's entirely possible that during the time you did your test, all of your customers were not online. You didn't have the peak load, right? So 10 to 15% of buffer is kind of recommended whenever you do some kind of testing. George Orwell had said that some people are more important than others, and in Kubernetes you have some service is more important than another service. And how do you do that? You do that with priority class. For example, again, let's say if you have a front end, back end, and a log analytics on your front end. Front end and back end should not go down, but if your log analytics is down for 5 minutes, the world doesn't crash. So it can go down. So that's how you define that one service is more important than others. You can do this with priority class and QoS. So in priority class, you can assign a numerical priority value to your pods. Higher the priority number, the more important that pod is, and it is less likely to be preempted during any kind of eviction. And QoS, Kubernetes assigns QoS to all of your workload, irrespective of whether you set it or not. And there are 3 values: guaranteed, burstable, and best effort. What is guaranteed is very less likely to be preempted or evicted. Burstable is more likely to be preempted, and best effort is YOLO. You only live once. So what is guaranteed? You have to have limit and request both set, and both of these limits and requests should have same number. In burstable, you may have limit but not request, may have request but not limit, and the values can be different. And in best effort, you don't define anything, right? So that's how, QoS is automatically set, and there are multiple ways by which you can actually tell kubelet to manually modify the quality of service for your applications. There is a very good talk in Cloud Native Rejects 2025 in EU about this QoS class that talks about 30 minutes. I recommend checking that out. All right, so now we come to the fun part of our cost optimization. So as I said, we run our clusters entirely on spot instances, not on demand. This is very, 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 very cost effective, but at the same point of time, it brings a unique set of challenges. And what the challenge is that the instance can go down at any point of time, right? So it's about trade-offs. There is no single, silver bullet by which you can balance this. It's actually not even a technical decision. It's actually a business decision. So you bring down your cost, but at the same time, you risk your availability. So however you want to run it. Termination of spot instances is inevitable, but you can actually try to circumvent this with different kind of solutions that are available in the industry. The most important and the most used is having multiple instance types. So again, this is a screenshot from our kOps cluster itself. As you can see, we have all these kind of instances running. The important point is that you should have different kind of instances, different families of instances, and different generations of instances. You should mix all of these things up together, right? Then only you will have the desired effect. Because I have seen that even if you mix all of them together, at any point of time, if you have a single type of instance, 7 instances get terminated at once, because you never know how these things are going to be terminated. So I recommend having as many instance type as you can with this kind of calculation. The second thing is that you have to decide your spot allocation strategy. In this screenshot, in the last line, you see spot allocation strategy is capacity optimized. There are 2 spot allocation strategy. One is lowest price, and another is capacity optimized. Lowest price means your R-scaling group will pick up instances that are lowest price. You get very cheap, but it also comes with a very, very higher risk of termination at any point of time. And capacity optimized is a strategy by which you tell AWS that I want the optimally chosen instances that have a less likely chance of going down. Then, since we are entirely run on AWS, we have a very nice tool called Node Termination Handler. And if you run Spot and Kubernetes, not on Spot, it works on on-demand as well. I highly recommend checking this tool out. So before a spot termination, AWS sends something called a rebalance recommendation event. Rebalance recommendation event that comes way earlier, most of the times, before the actual spot termination. And what NTH node termination handler does is it captures that event, and then it processes that event and cordons and drains the node for which the event has been captured. So you have way more higher chance of gracefully shutting down your workload and taking them to elsewhere, right? If otherwise the time window for a spot termination is only 2 minutes, so in 2 minutes you cannot move all of your applications to another node, but with the help of node termination handler, you get a much wider time frame and you can do all sorts of things, gracefully terminating the pods and moving them elsewhere. So in this screenshot, you see that this particular node, the middle node, is ready, but scheduling has been disabled, so no new workload can be put up on this one, and it has already been drained. When you should not use Spot, when you have a long-running task that cannot be interrupted, you should not use Spot. All right, and if you run some sort of environment where you need 100% availability and nothing can go down at any point of time, or you cannot, tolerate failure, you should not use Spot. It's as simple as that. So this is particularly, I don't know whether this is available for other Kubernetes flavors or vendors, but this is in particular available in kOps. And if I go back to this thing, you see there in the second last line and the third last line, you have on-demand AVAP base and on-demand base. So on-demand AVAP base, it means that what is the number of the instances that you always should have on demand, right? So if you have 10 instances and the number is 2, that means that 2 instances will always be on demand, right? And the rest can be spot. And on-demand base is kind of a percentage value that determines how many, the ratio between on-demand and spot. If it is 100, then it's all on demand. If it's 0, then it's all on spot. So in this instance, we have run on all on spot. That's why on-demand base is 0. So this is particularly useful during a scenario where your spot instances are terminating very quickly. You don't have any other solution other than to move on demand, right? Because you have to run your application. So that's how we use this particular thing. Now, this is an unique scenario for us, is that we found out that, how much time? Okay, so we found out that our production clusters cost some money, but our test clusters cost way, way more than production. And why is that? Is because our developers run something called a preview environment or a PR environment, by which you do a CI on Jenkins, and then ArgoCD creates a complete replica of the actual production application, right? By which you can test your code very reliably. But that means you also have all the pods running in the production application similar to all the time. And the problem with the PR environments is that developers only work 8 hours, more or less. So you don't want your PR environment to stay up 24 hours. That's wasting money. Why do you do that? So you need to have a mechanism or a tool by which you can reliably downscale and upscale these PR environments, in our case namespaces, on a schedule. When developers are working, these things should run up. When developers are not working, these things should be turned down, right? And this particular work of scheduling of downscale and upscale is handled by something called a project called py-kube-downscaler. When we started to use this was written in Python. Now they are actually running a Go version of the same application. How does this work? So again, screenshot from original use. There are only 3 important, this is a config map, 3 important values: default downtime, default uptime, and exclude namespaces. What is default downtime? Default downtime means when your applications or namespaces can be made unavailable. So in this scenario, we are telling that from 6:01 to 11:59, and then rest of the midnight to that time, you define the default downtime. Why default downtime is spread like this? Because in this particular software, you cannot have overlapping day and time. So from 6 p.m. to next day 4 p.m., that's actually 2 days, right? So you have to spread out the days in each unique day. Default uptime is when you want the applications to up, and exclude namespaces is something that you don't want downscaler to downscale those kind of things. So you see that there is a thing PR6428, which is a PR that our developers didn't want to go down, so we have excluded it, and it doesn't go down anytime, right? So this is a very useful tool, actually. And we thought that everything is nice, but it's not. And why is that? We found out that the downscaler has downscaled the replicas, but the number of nodes didn't go down. It should have went down, because autoscaler should come in and kick out the nodes that are less utilized. And why is that? Is because we use Argo. So Argo is GitOps. Argo is finding out that I should have 2 pods running inside the cluster, and downscaler has scaled down to 0. So Argo again starts those pods up. So downscaler is downscaling and Argo is upscaling. Argo is trying to get it back to the intended state. So in this constant battle between these 2 tools, we're actually achieving nothing. The cost is not being saved, and at the same time, the PR environments are not running. This is like a catch-22 kind of scenario. So how we solved this problem? After significant amount of time spent in Argo, forums and Slack, we found out that this is a very common request in ArgoCD GitHub project. ArgoCD doesn't handle this thing, but ArgoCD has something called a concept of sync windows. So sync windows actually let you handle when your application should sync and when your application should not sync, right? With sync windows, things are relatively under control, and this is a sync window. Again, screenshot. So in this thing, we have 2 sync windows. One is allow and another is deny. So allow has a schedule and deny has a schedule. So the trick is that you have to combine this sync window with the downscaling period, right? So during the downscaling period, it is not going to try to sync. So the world is very nice at that point of time, because these things are not fighting with each other. And deny always overrides allow in this particular scenario. So this is how we actually achieved a relatively calm period of downscaling. Disclaimer is that we are slowly moving away from the downscaling. We have found out another thing that is handling these things more gracefully with a GitHub action, but we are still researching. So this is how we do this. Now, the number of pods has went down, so the requirement on the nodes has also gone down. So how do you terminate the unutilized node? we use something called cluster autoscaler. I mean, everybody's aware of this. So cluster autoscaler, you tell when the node utilization is below a threshold, you can remove those nodes. So we do that with this thing. So in this screenshot, you can find out that when the scale down utilization threshold is 0.6, that means 60%. So when the utilization has fallen below 60%, we kind of terminate or remove the node. And all these things are kind of present in the documentation, not spending time. If it happens that if you have a pod and you want that that pod to stay up, in our case Jenkins, to stay up as long as the job is running, you had an annotation for that particular deployment of pod so that you do a safe to evict false. With this annotation, you tell cluster autoscaler that please don't take this pod as long as its job is not done. And when this is scaling down, when scaling up, what do you do? So scaling up, you should look into a concept called expander. So I think there are 5 expanders. I don't remember all of them, but we use this thing called expander least waste, which means that during scale up, we want to waste as less memory, CPU resources as possible. So we have picked up this number. So that's how we do cluster autoscaler. What's next? We are looking into several other different things. We want to replace cluster autoscaler with Carpenter altogether. We are not doing that at this point of time because we have to upgrade Kubernetes. We run Calico as CNI. We want to move to Cilium and Hubble for the observability thing. OpenCost for cost reporting, Descheduler for running more compact servers, by which you can deschedule, you can compact pods into a single node. Kyverno Inspector Gadget, this is a very, very nice tool from Microsoft, which allows you to have very eBPF-based, very fine-grained kind of observability into your cluster. And we are also trying to get, customized for a post-Helm rendering thing. That's pretty much all that I have. And that's kind of, we are also 2 minutes. So this is my LinkedIn. If someone is interested to connect, that's all fine. I mean, I actually took a screenshot and put it there. So that's all. If you have any questions, I'll be more than happy to take. That's all. Thank you. Cool.
So any questions?
In the future, you are showing something about Cilium and Kyverno, right?
Right.
What is the difference between these two? As far as I know, I think Cilium and Kyverno does
No.
the same thing.
Cilium is actually a CNI, similar to Calico and Flannel, all those things. So we run Calico as the
networking type.
Networking, yeah,
okay.
for networking. And Kyverno, by which you can write policies, write Kubernetes native policies. Like you can do multiple things. So for example, the downscaling on schedule, right? You can perform similar kind of task with Kyverno as well. So you write a policy and Kyverno will mutate your pods. So Kyverno is a, what is called, post-mutating application. So Kyverno will come in and mutate your application after everything has been done. So that's, when Kyverno is a policy engine and Cilium is a CNI solution.
Thank you.
Any other questions? Because you look like, what the hell just happened? But I think that it was a very interesting topic. So any other questions?
Did I go too fast?
Excuse me?
Did I go too fast?
No. I think that you went well. Actually on time, so
Yeah.
everything was good. Is here somebody who's using Kyverno? No? I'm disappointed. One hand or?
Yeah, there are
Only
some
one
people.
hand? Okay. So or Open Policy Agent or OPA? So we have
Yeah.
serious security issues here.
Oh, yeah,
That's, I'm like, whoa.
we have more hardcore
We have
people.
lots of education to do here in this country. So actually, I recommend to check Kyverno or Open Policy Agent because that will say how your deployment can look like. And if it doesn't look a specific way, you will not deploy. This is a very good check for the production.
Yeah. Cool. Okay. Thank you, everyone, and enjoy the conference.
Yeah. So, and thank you so much.